let's maybe start by welcoming Alexis Schotte from IBM, coming from the West Coast. So it's quite early on your side. Thanks for coming at this early time of day. We very much appreciate that. So Alexis has several interests that are like close to our heart and has thought quite deeply in particular about tensor network models and tensor network approaches to phases of matter or phase transitions in various kinds of topological models, in particular string net models on the one hand. And he also shares our interest in notions of quantum error correction. And we'll bring these worlds a bit together in the talk that is about to come, where we learn about universal Fibonacci Turaev-Viro codes, where tensor networks and notions of quantum error correction come into play at the same time. So thanks for coming, at least virtually. And yeah, the stage is all yours.
Okay, well, thank you for this introduction. Okay, well, I will dive right in. The talk should be about an hour, but it can fluctuate strongly depending on kind of how much time we take to delve into details. But there's certainly a lot of room for discussion afterwards, so we should be fine. Okay, so well, this talk, well, can you see my screen to begin with? That's all good. Okay, I see thumbs up. Okay, so this talk will deal about quantum error correction, and specifically non-abelian quantum error correction using string nets, using Fibonacci string nets. So this was joint work with Guanyu Zhu, Lander Burgerman, and Frank Verstraete. The latter two being in Ghent, and well, me and Guanyu currently being at IBM here in Almaden in the States. So I will start my talk by some general words on non-abelian quantum error correction, why we want it, why it might be interesting to study it, and what the differences are with abelian and topological quantum error correction. Then I'll do we'll have some discussion on the model specifically that we use. As we use a slightly modified string net model, we'll talk a bit about this. We'll talk about a related kind of continuum view of this called the ribbon graph Hilbert space. Then we'll speak about specifically or methods for the quantum error correction using this model, about classically simulating this, and then we'll kind of wrap it up in a little summary and some outlook on future directions to study. Okay, so topological quantum error correction is an idea that originated in the late 90s, in particular, well, amongst other by Kitaev, who proposed that we could use anions to do fault-tolerant quantum computation. The idea here is that these anions are in a way intrinsically topologically protected, and now you could do computation by braiding and fusing them. And so from this came then the idea to do quantum error correction with them. But in general, there's kind of two ways where all this topological quantum computation stuff can go. The first is what we call passive topological quantum computation. The idea here is to use the anions themselves to do the computation. So you would have some system in which the information is encoded in the ground space. And then you have this intrinsic energy gap if you work at zero temperature. So if you work beyond zero temperature, you'll need to protect still against thermal noise, but you'll have these excitations which appear on top of the ground states, which can be non-abelian. And herein, you will either do quantum computation or you'll try to encode some state to protect it as a quantum memory device. The other approach, kind of the opposite of this, is the active quantum error correction. So here you will have a system of qubits on a lattice, typically, and then you'll have some code space which is defined by measuring a set of stabilizers and wanting the result to be one for all of them. So you're actively measuring a set of stabilizers, and then whenever either of those are violated, you will actively try to correct it. The important part here is that you're working with a system of qubits in the active one. In the passive one, you're working in some system which inherently has this topological order embedded in it, such as Majorana wires or quantum fractal Hall states. So what we want to do is kind of something between the two. We want to do active quantum error correction, but we want this to be non-abelian, because all these other active quantum error correction systems here are abelian. So we want a code space that is a system of qubits. We want to actively measure a set of commuting projectors. And we want noise to create groups, well, pairs or triplets or quadruplets of non-abelian anions. Much like noise in the surface code creates pairs of abelian anions, well, we want to generalize this to non-abelian anions. So with this in mind, two goals that we work towards. The first is the construction of such a code, so a non-abelian code of qubits. And then the second part is simulating this code in order to obtain a threshold to prove that this code is worth something and could potentially, I mean, at some point in the future, be interesting to implement or, you know, influence the implementation of some related code.
Can I already ask a question here? So, I mean, like clearly, I mean, it's part of the model that the excitations are non-abelian onions. I mean, you're about to explain that in great detail, I'm sure. But when you say noise are non-abelian onions, so of course the noise does create them, but will you say more about the underlying noise model that you've picked?
Oh, sure. So we will, since we want to kind of be able to compare this to the classic stabilizer codes, such as the surface code, we will have the noise be essentially just depolarizing noise. So okay. Just want Pauli errors to be able to kind of benchmark it against other codes. As you will see, I mean, this will be discussed extensively in the talk, but choosing Pauli noise on the specific model we do will be kind of unnatural in the way that this will be, it won't just commute or anti-commute with everything as it does in the surface code. Mm-hmm. So we will work with just Pauli errors, but we will need some tricks to understand what that means in terms of the system we have. Mm-hmm. There's a lot of work, but I'll mention some works later, where they study non-abelian quantum error correction, but instead of having a model of qubits and Pauli noise, they have a kind of phenomenological system where you say, well, imagine we have this lattice. Well, we have like a bunch of tiles which live on some torus, and noise creates a pair of anions which stretch across the boundary of two of such tiles. Then we can try to do error correction with this. You can kind of make a phenomenological model where you say that noise is the pair creation exactly. We kind of take the opposite approach, where we have to figure out what noise means in terms of anions, but it has a very clear meaning in terms of what it does on the qubits themselves. We'll come back to this later.
Okay, we'll come to that. Okay, just ask.
Oh, some more questions or?
Yeah, so you just mentioned that, like, I mean, depending on what noise you pick, it's easy to analyze or hard. And it's clear. So, but I mean, if you were to consider this highly artificial noise of, okay, sort of, I have some probability of a pair of anions being created. Isn't that kind of the same as like Pauli noise on a surface code, for example? Because there, it just so happens that phenomenological Pauli noise is like the same as pairwise anion creation.
Yeah. So
yeah. So if you have this, yeah. So for me, it always seemed like choosing this artificial noise from like or anion noise is sort of, you don't gain anything from it by construction, basically. So, but you said that it would also be interesting to get, like, do the same for this type of noise, like the same analysis, or did I understand you wrong?
I'm not sure if I completely got your question. So Do you
Because
mean
it depends
that,
on,
like, why would we choose the Pauli noise if it's so bizarre here? Or do you mean, could you do could you pick a noise model which corresponds exactly to creating a pair of anions?
Yeah, so my question is that I thought that if you were to choose a noise model that would just create, like, where the sort of the elementary constituents are creation of a pair of anions, then I don't see a difference in like other topological codes, like
Oh,
Pauli codes.
I see.
So I wouldn't even like, I always thought it's not even a fruitful way to spend your time to analyze this, because you just change your basis and then the problem looks exactly the same as in the surface code.
Oh,
But
well,
I mean,
so
for non-abelian
But-
anions, it might be different.
Yeah,
that is,
I mean,
that is a
just
very
for-
good question.
I mean, just for clarification, maybe we should understand what you mean by depolarizing noise. Do you mean depolarizing noise as in applying Pauli, like random Paulis, as in like
Yes.
standard depolarizing?
As you will see, the noise model will just be applying Paulis on the qubit. So really, we have a bunch of qubits on a lattice. So our code is very similar to the surface code in a sense that it's also a bunch of qubits on a lattice with some vertex conditions, with some package conditions, which you measure.
Right.
And so the noise is really on each of these qubits, you will apply Pauli X, Y, Z with set probabilities.
Right, but the string operator of your model is not
No, the string operator
corresponding
is
to the
extremely complicated. It's very different from just Pauli.
Yeah.
And so it's not reasonable to choose this string operator as your natural noise model is that this doesn't act on individual qubits. The string operator has a much trickier form.
But then once you measure your stabilizers, you have to collapse down to some of these string operators, right? Because you're projecting down to some eigenspaces of stabilizers.
In a sense, to a superposition of these different string operators, in a sense. We'll analyze this in much detail later, because this was an important part of the work was finding a way to understand some explicit noise model in terms of individual qubits, to understand this noise model in terms of the creation of anions, because these seems to be very difficult to relate, because excited states with a certain anion contents are extremely complicated to write down because there's these highly entangled states. So finding a kind of a relation between these two is important. To go back to the previous question about why this is different from the surface code, is that the type of anions that they created have very different properties. Notably, well, most importantly, I think, they don't have fixed fusion outcomes. So in the surface code, if I have two like E particles, if I fuse them, I know for sure they will annihilate, always. That's the rules of the game. They will annihilate if I bring two of them together. Meanwhile, here, if I have two Fibonacci anions and I bring them together, they might annihilate or they might create a new Fibonacci anion, and that changes kind of the dynamics of the game completely if you don't know the fusion outcome beforehand.
Okay.
Okay, we'll come back to all of this. All of this will reappear in the talk in much greater detail. Okay, so where was I? Okay, so our two goals, right? Constructing the code, simulating this code to find a threshold. So we kind of combine three ideas here to make all of this work. So there's of course a lot of ideas from quantum error correction. Then there is some ingredients from topological quantum field theory, which we will need to understand what this means in terms of anions and to understand the relevant states. And then we will use some tensor network methods too. So we kind of combine these three fields together, and nicely in the intersection of these three is where this talk is happening. And we really needed all these three ingredients. There seemed to be no way to do it with only two of them. So a quick comparison. If you have abelian and non-abelian codes, kind of the active kind, like what's the important difference? What's the pros and the cons of all of them? So the good things about abelian codes is that they're local low weight stabilizer codes, which are very convenient to simulate. and relatively convenient to implement, it seems. So they've been very well studied, and they have very high thresholds. So all of these are, of course, very desirable properties. The big downside is that in 2D, there is no way of natively doing a non-Clifford gate. And by which I mean that just you have to add some extra ingredients to be able to do universal computation on your encoded states. So this is done either through magic state distillation or to code switching to like higher dimensional codes. And both of these come with a certain overhead, which you would love to avoid. This would be great. Non-abelian codes, on the other hand, are universal by nature, like natively universal, by just deforming, or by doing some code deformation without switching to higher dimensions or needing some state injection. You can still do universal gates. And they're a way to go beyond the paradigm of stabilizer codes, which is something people have been wanting to do for a while anyways, to kind of break free from these restrictions from stabilizer codes. The big downside, of course, is that the price you pay for these two things is that they're very complicated, meaning they're also extremely hard to simulate, even so that for a long time it seemed that there was just no way of simulating them. We will show that there is a way, after all. So this work builds on a bunch of previous works, all of which are very important kind of in the literature on non-abelian codes. One of the main ones is the work by Koenig, Kupperberg, and Reichert on non-abelian codes, as called Turaev-Viro codes. So important that we even put this in our title. So I highly recommend you check this reference out. Bohnstein and De Vincenzo did some important work on finding circuits to measure certain operators that we'll need to measure. Feng and Bohnstein. Well, Feng was a PhD student of Bohnstein and wrote a dissertation which includes some elements very similar to things we did on fixing certain violated vertices. We'll come back to this. And then there's been some work on phenomenological models, amongst other by Burton, Brett, and Flamia. So these are the models I mentioned where noise is simulated as pair creation of anions. And so they have been studied amongst other by these, also by Poulain and Dauphiné is another important one. And then there's the work by Nick Butlink and collaborators on tensor networks for non-abelian anions. Well, tensor networks for anion models kind of in general, and we'll take some inspiration for that as well. Okay, so let's talk about the model that we use specifically. So we base ourselves on the Levin-Wen stringnet model. So this is a model where you put anions on edges of a lattice, a trivalent lattice, and then you have two kind of operators which are defined by a unitary fusion category. So you pick some fusion category, which is this mathematical object which has some properties. It has a bunch of string types. So let's say they go from 1 to n, and these determine the possible qubit state or qdit state. So in our case, we'll choose a category with only 2 string types, which means we can use qubits. These string types have some branching rules, and these branching rules determine the vertex terms, meaning in every vertex, only certain types of strings are allowed to meet, essentially. For example, in the surface code, your category is such that only like an even number of non-trivial qubits can meet in every vertex. And then this category also has some numerical data called, well, the quantum numbers, the quantum dimension, I mean, and the F symbols. These are some mathematical object again, and these will determine the plaquette operators. So with the right type of category, this is exactly the surface code. So if you choose Z2, you'll get the surface code, and there your ground state will be superpositions of closed loops of where the dark lines here are the qubits in the 1 state, and the clear lines are those in the 0 state, and then you'll get these closed loops and then superposition of all possible configurations as these ones. We will choose a different one. We would choose the Fibonacci category. And now we have closed loops, but with branching. This is an important difference. So with branching, and then we get superpositions of states as below here, where you have all types of branching loops. So our fusion rules are that two qubits in the one state can meet in two different ways in a vertex. Either there's 3 of them that meet, or there's an even number of them that meet. So we will use a slightly modified version of this called the extended stringnet model, where we will add extra edges in every plaquette as so that we add a kind of a tail edge in every plaquette. The reason why we do this will become clear very soon. And so the operators are more or less the same. And the plaquette and the vertex operators are exactly the same. The plaquette operators are the same after you say in the ground state, we want all these tails to be in the trivial state. And so in this model, we will see that localized excitations will follow doubled Fibonacci anion statistics, meaning if you have some excitations, you can associate them after some measurements to a specific anion type. And also inside a single plaquette, we can measure the anion's charge of a single plaquette, provided that no vertices are violated. So we will talk a lot about what we call the stringnet subspace. And this is the subspace where all your vertex conditions are satisfied. Your plaquettes can do whatever, but your vertices must be satisfied. And then within this ground state, you can measure the anion content of a single plaquette. So before we talk more about this model, we will quickly discuss an associated kind of continuum model. And then after that, we will be able to use it to more or less interchangeably. So this model seems kind of related to the stringnet model because, well, it is very related, of course. So we also start with a fusion category with some labels, some fusion rules, some data in the form of quantum dimensions and F symbols. And then we'll start with some manifold with a bunch of punctures. So on the figure below here, the punctures are represented by the darker gray little circles with the dots on them. So on every circle, you will mark one dot, 1 point, and then you will look at directed graphs, which can branch, so only trivalent branching, and they can end only on these marked boundary points of these punctures. So you'll get some graph-looking thing as in the figure below, and then we consider the Hilbert space of all these graphs with labels, such that the labels satisfy the fusion rules of your category, and such that, well, you consider linear combinations of these, but modulo some relations. You can kind of deform them continuously. Closed loops which do not enclose a puncture can be removed. You cannot have tadpoles. And then you can kind of redraw your graph using some equivalence relations which we call the F move, which is the bottom relation here. So you'll have just a linear combination of different types of branching and structures, but all these lines can only end in these marked boundary points. So we will be able to realize this Hilbert space of combinations of such graphs on a lattice as well. So that's kind of the okay, well, it seems, sorry. Okay, I thought I had a wrong figure here for a moment. Sorry for the confusion. So the way we do this is we start by some manifold, and then we add punctures everywhere where we would want to have our plaquettes later. So if we have something with n plaquettes, then we would have n punctures on our manifold. And so we would have these lines running kind of through them, sometimes ending in them. And so we start by first drawing kind of our lattice, just in our mind, I guess, around these punctures. And then we will deform these lines, which we could freely deform. These were kind of the plain rules of this Hilbert space anyway. And we deform them to lie on all these edges. And this is essentially all you need to be able to relate these two Hilbert spaces. So on one side, you'll have this ribbon graph Hilbert space living continuously on this manifold. And on the other side, you will have this stringnet Hilbert space of on our lattice. So you'll have the Hilbert space on the lattice of all these qubits, where you just need to impose the conditions that all vertex conditions are satisfied. So sometimes you will have graphs which don't seem to fit on these lines. The reasoning here, though, is that you can always restructure these graphs using these F moves. So you can always get to something that will fit on these lines to relate it to Hilbert spaces. So with this said,
could I ask a question? Is it obvious that every continuum ribbon graph theory naturally admits a lattice realization, or is it only in the case of you possessing this unitary modular tensor fusion category that this lattice realization is imminent?
I think you need to, well, it's certainly required to have these F moves. So I don't know about kind of the most general case. But what you certainly need is kind of this way of restructuring them. Because this relation essentially means you can always get them to the right shape to fit on this lattice.
Yeah, okay. So this is what I meant. So apparently it seems like because of the existence of this F symbol, you are able to properly embed your manifold.
Yeah, I think
deform them. Yeah. You can make the weirdest shape, right? I can add just an infinite amount of complication if I want, which can always be removed, it seems, but only because I have this F move.
Yeah,
I think it's modularity.
Sorry?
What did you say?
It's modularity, just as a comment, it's a modularity that you need. Like, for example, there's the Semyon category, which has two elements. You could say vacuum and a single Semyon, and this doesn't admit a lattice realization on a compact manifold.
Oh, that's very interesting. I would love to put some references on that later, on like the general case.
Yeah, the reference is actually just a private conversation with someone in our group who knows, but I can relate the question to him and he will give me the reference if you are.
Yeah, that would be interesting.
Yeah.
Andy's not in, right? Do you know where?
No, he is in the US, but he's working. So it might even be better for you, Alexis, to get in contact with him. I don't know where exactly, but I think most of the time he's at the East Coast right now.
Okay,
that's pretty far.
No,
but he was also in Arizona last week, I think.
Okay, well, we'll find.
Last I heard he was in New Mexico.
Yeah, look now.
But I guess I suppose all progress is made at some point. At some point in all progress, the only reference is some private conversation, probably. So.
Yeah. I was just asking because not every continuum field theory admits a lattice description, and not every lattice theory admits a continuum description.
Yeah, but also not every tensor category gives you a continuum TQFT.
Yeah, that's true. There are some quantum field theories that cannot be written on either the lattice or in the continuum. That's true.
Wait.
No, but that's even true for, even non-topological field theories, right?
Yeah.
There's this insightful article by Tobias Osborne on continuum limits, which is a great read. That cures you from any misunderstanding of how easy it is to do continuum limits from lattice models.
Luckily, this one does admit a nice continuum limit, which makes our lives a bit simpler because then we can draw nice pictures. So this will be very helpful. Okay, so the lattice relation, this is behind us. So a thing we will need, and which will be pretty important, is the fact that this ribbon graph Hilbert space has a pretty interesting basis that can be constructed, which we will call the anionic fusion basis. So the goal is to have some basis of this ribbon graph, which transforms nicely under the following deformations. So Dean twist, where you take a puncture and you grab it and you rotate the whole thing by 2 pi, deforming all the graphs on the manifold as well, or a braid move where you would take 2 punctures and then just deform them such that you wrap them around each other, also deforming all the lines with this. So kind of the computational basis, which corresponds to the computational basis on on your equivalent lattice realization is extremely unnatural for this. Just if you do the twist, it's not diagonal in any way. Things will be pretty ugly. But it seems that you can form a basis which has the interesting properties that these basis states seem to be exactly related to fusion states of anions in the doubled category. So I will not discuss the exact construction here since it's pretty technical, but I can give some references. It's very well discussed in this paper by Koenig, Kupelberg, and Reichert.
Yeah, but that's a true isomorphism, right? Between the the two.
Yes, it's also mentioned it's also explained in the appendix of the paper related to this talk. But we got this out of this from this paper by Koenig, Kupelberg, and Reichert.
To be fair, it's a long paper. I mean, your paper.
Yeah, it is very long, but there's a long.
Quite heavy and long and winding. It's super interesting, but it's also quite long.
So the important thing here is that basis states are related in this special basis are related to fusion states of anions in the doubled category, and so the double category here is always braided, so you always get anion statistics, it seems. But specifically, the one we choose is modular. Meaning that the double category has this very nice structure, which is just 2 copies of your input category in a way. So we will have these doubled labels, which is just 2 copies of Fibonacci, and the 2 copies must independently satisfy the fusion rules. So this anionic fusion basis, we will, since we kind of have this equivalent continuum theory, we will take the freedom not to draw the lattice all the time. So the anionic fusion basis corresponds then to just specific fusion trees and then different labels of different ways of labeling these fusion trees with doubled Fibonacci labels, with the addition of an extra tail label. So states will look as follows. We will have all the labels of the edges. So all of these bold labels are in fact 2 labels. They're a pair of labels. They're like these 2 copies of Fibonacci. And then these L labels are extra tail labels. And what these need is that they must satisfy an extra kind of set of fusion rules, which is just, again, your original fusion rules, but with the 2 copies. So with the double labels ending in a specific puncture, you have this kind of what we call the top and the bottom layer, the plus and the minus, and they must fuse correctly into this tail label. This will become maybe a bit more clear later, but these tail labels will be the ones ending in these extra edges we added to the lattice. So, so as you can see kind of in the bottom picture, the tail labels are the ones ending in this extra qubits we added to each plaquette, and then the other labels are kind of just the ones wrapping around. So these double labels can be translated to single labels, and then you get like a very tricky linear combination of objects like this, where all these labels are just now normal Fibonacci labels. So you just have 1 and tau, just the 2 labels for each of these edges, but you just get a very long linear combination. Again, the specific coefficients for this are given in the paper, but I won't go into detail on them because that would take us too far and make this a bit too technical.
So just to be sure, the non-second labels, you said it's just the doubled.
The bold ones.
The doubled Fibonacci label, but I somehow thought that sort of the right-hand side of this equation is sort of written in the computational basis, but now you say it's sort of 4 labels.
Well, okay, no. So the left-hand side. Okay, so it's good that you mentioned this wasn't exactly clear. So the bold labels. So the red lines with the bold labels on top. These represent these doubled labels. So this
because these are really
nice
the
indicate that this is a state which looks like a fusion tree of a bunch of doubled anions. The bottom one is saying we can write this in the computational basis. That's the bottom one. So the bottom one is this fusion state written in terms of the computational basis. However, for this, well, this becomes a very long linear combination with a lot of tricky coefficients, but you can do this. The important fact here is that it exists, because we won't calculate much with these labels because they're very complicated. But since we know they exist, we'll still be able to do things with them.
And it's an isometry, I suppose, or something, like you have some.
Like these equalities, just these are.
I mean, yeah, you can sort of not only relate the anion states to the computational basis, but also vice versa. That's sort of
yes,
what I was.
Yes, it is. Yeah, indeed. It goes both directions. It's just it's just a basis transformation, if you want. So this is one basis state in the fusion basis, and this is equivalent to a linear combination of basis elements in your computational basis. So now that we have this nice way of writing these fusion states with these red lines, we'll take the freedom to sometimes show things like this, that on a torus, instead of drawing these super complicated computational basis states, we'll just represent the basis with these red lines. So on a torus, you have a little bit of extra complication since you have non-trivial loops that you could form. So your fusion state must include a handle, which is this red line wrapping around the torus. So again, this can be written in terms of your computational basis, but will just be very complicated and not necessarily very pretty to look at. So this handle label is exactly what makes you able to encode logical information in this. So the logical state corresponds to your handle label. Also, you can in principle choose your handle label to wrap around the torus in different ways, because there's two choices here to be made of non-trivial loops. But they're related by some transformation as well.
Will you say more about the encoding of the logic information into the handle labels or the respective dimensions that you encounter and so on?
Okay, so in our case, the information, well, you're able to encode, as in the surface code, 2 logical qubits. And the way you can see that there's 2 is that these double labels, they're double Fibonacci. So let's just go over them. So there's 1, 1, which is, well, the trivial one. So no handle, essentially. Then there is 1 tau, there is tau 1, and there is tau tau. There's 4 ways of labeling this handle label. So these you can just choose these 4 as your encoding. Yeah, that's kind of a short summary of that. So the handle labels that, well, of course you can change them, and they change exactly if you have some process which you can understand as a pair of anions wrapping around the torus and fusing after that. So for example, here you have 2 pairs of anions, and we'll bring 1 member of each pair along different parts, along different paths, which in total will kind of wrap around the torus. So this would constitute like a logical error, like 2 pairs of anions being created by some noise, and then the decoder failing to recombine them correctly and wrapping one of them around the torus. So this is the kind of processes that we want to avoid while decoding. So
that would create like really literal logical errors while decoding.
Yes, this is exactly what is kind of a logical error.
Yeah, okay. Wonderful. Yeah.
Okay. So these fusion states, again, since we know there's these were kind of drawn in this continuum picture, but we know we can put them on the lattice as well. So this is the nice thing. We don't always have to deal with states like these, but we know they exist. And the way you would kind of get them is, well, again, you would draw your continuum state more or less on the lattice lines, and you would deform it. And then you would just get a very complicated superposition again, in terms of the computational basis, which we would draw like the bottom half of this, where all these lines don't lie exactly don't follow exactly the same pattern as your lattice. But as I mentioned before, you can solve this by doing F moves to change the shape of all these lines until they do fit correctly on the lattice. So you can always do sufficient F moves to resolve this whole thing to fit exactly into the lattice. and then you'll reach the state you want. By the way, all the dotted lines here, the dotted lines represent the application of the plaquette projector. Yeah, well, they'll appear at some point later in a different shape also. But to kind of simplify the notation, just the dotted circles represent the trivial plaquette projector.
I mean, you could equivalently. So this is sort of a question if this is the case. So could you equivalently just make every line that crosses through a vertical line at the plaquette a trivalent, like having a trivalent vertex where the boundary label could also be the trivial one? Because that's sort of, is this what is like implicit by this dashed line with a straight red line going down without an additional dangling edge?
I think I misunderstood your question. Could you ask it
So,
again?
yeah, sorry for my confusing.
Yeah, it's hard if you
today.
cannot draw it.
So
yeah,
so you can't see my mouse, right? No.
Wait, I can't see your hands moving or anything. I can only see a few people. Wait, maybe I can.
Oh, anyway, so I'm looking at the picture with the red graph, and then close to where you wrote B in boldface, there is a plaquette right of it.
Yes.
With the dashed line. My question is this just to not draw these horizontal dangling edges at every plaquette?
Yeah, so
because you could you equivalently, instead of drawing this dashed line, just have like one dangling edge for each plaquette where you just have a vacuum label sort of.
Yeah, so the dashed line do something extra. So okay, indeed, it's a good point.
That's okay. So it is not the same.
Yeah, but I've taken the freedom not to draw these dangling, these tail edges everywhere. But it is true that if there is a dotted line, this implies as well that the tail edge must be 0. So I've taken the freedom not to write them to kind of simplify the drawing, because it's a lot of lines already. But yes, so whenever a plaquette contains the vacuum charge, we indicate this by this dotted line, but this also means that the tail label must be trivial.
What is additionally fulfilled when this dashed line is there?
The projector is applied, and the projector we'll see in a moment. But it's kind of as in the surface code. If your plaquette is kind of in trivial state, you know that this corresponds to like a 1 plus XXXX type of projector.
So does it enforce the sort of what I think you call it stringlet subspace on every vertex around the plaquette, not only where the dangling line is?
This drawing kind of already implies that the vertex condition is satisfied, because there's nothing to break it, right? To break the vertex condition in the Fibonacci case, you need a line to end in a vertex somewhere, just one line ending there. So this is never the case here. Well, because I mean, why can't this be the case here? The reason for that is that this correspondence between the continuum model and the lattice model only relates the subspace with no violated vertices. So all we're doing here is finding a map between the continuum model, between this fusion basis of the continuum model, which must have like an equivalent basis in the lattice model. And this is a basis for the subspace with no violated vertices specifically. Does that kind of solve your question? Because I know it's a very technical subject.
Yeah, I mean, I can also postpone it. It didn't quite answer it, but it gave more information than I had.
It's not clear in a few slides. We can get back to it and kind of discuss some more about this. So again, here the important thing is not that you will rarely write this superposition as a whole, because this is this super entangled, very tricky state. But we know we can make it. And this again is something that will come in handy. So
I had another question. Can you always efficiently go from a continuum description into a lattice description using these F moves?
Well, efficiently, I guess it depends how you define efficiently.
I mean, like in the system size.
What would that mean?
So
I'm not
the
sure.
F moves. I mean, the F moves are only defined, like there are continuum analogues of this, but the F moves themselves are only defined on a discretized space.
Yeah, exactly. I wouldn't quite know what the F's move are in the continuum, and I wouldn't quite know what it means to be efficient in the continuum, because that would mean that, again, up to some lattice description, and then the problem somehow goes away.
Yeah, you can make the lattice infinitely you can make the continuous model. You can write a state in an infinitely complicated way, right? I can add like, you know, a trillion of loops if I want, like a trillion of branchings, which essentially will amount to nothing if I choose them carefully. But I can just keep making things complicated by making bad choices of what looks simple to me. But yeah, but the F move is defined in the continuum though. The F move is some equivalence relation between two states in the continuum, because we have the continuum Hilbert space is linear combinations of this graph looking objects, which these trivalent vertices, up to like deforming them continuously and up to doing F moves, so that we can always kind of reshape things to fit on a lattice.
See, but isn't F moves in the continuum just, I mean, just continuous maps in terms of the topological space? Like, okay, I didn't know that people also call this F moves. I just thought.
Okay. They just redraw the lines if you change the labels correctly and maybe add a sum somewhere. But you're just redrawing the lines, and you can deform them continuously anyway, because that was also one of the rules.
Okay, fair enough.
Okay, so we will now kind of say some words about the tube algebra. So this is an algebra of operators which are defined as gluing some tube on the lattice. I've tried my best to make a figure of this. So you start with, you know, a manifold with a bunch of punctures, and I will take this tube and we'll glue it onto one of the punctures. And as a result of this, we still have a manifold with the same number of punctures, you know, because the tube had, well, two holes and one of them was glued onto another hole. So we keep the same number of punctures. So this is a map from this manifold to itself. And these tubes will have some lines on them, which will kind of, well, it's depicted on the top here, right? There's like one line going from bottom to top, and then there's one line wrapping around. So that gives you like these two vertices. And it seems that you can form a whole operator algebra with these. And then you can look at what are the idempotencies in this algebra. So how can you make projectors with objects like these with different labelings? So each of these edges in the Fibonacci case can be either trivial or can be tau. And it seems that the idempotent projectors are exactly the projectors onto the different anion labels that you can have. So so you can choose, for example, to project onto the ground state, onto the trivial label. And as one expects, this is precisely the same as this plaquette projector. So your plaquette operator, which defines your ground state, corresponds exactly to projecting onto no anion is present in every plaquette. But you can create different projectors, which will project on a 1 tau anion being present, a tau 1 anion, and a tau tau anion. And the tau tau anion itself then splits into into a sum of two projectors, which will be with the tail being trivial or non-trivial. So let me go back to the previous slide for just a second. So how do these projectors work? Is you have this this state with tails, and you kind of glue this tube in the middle here. No, actually, I have a better slide for this, which is just the next slide. Okay, so how do you apply these in the lattice? Kind of, because you can't necessarily do this gluing thing. It's not so straightforward in a lattice. But the way it works here is that it's just inside of one plaquette. And this is why we need this tail edge also. So what you'll do is just, you'll take some tube, which will indicate by this O, X, alpha, Y, beta, and you'll glue it to the inside. So you'll get this kind of snail looking thing. And now we can just do F moves until this has the right shape. This is the game with the F moves. So we'll do a set of F moves, and with each one we'll deform it. And we keep doing F moves until we have kind of a tadpole-like thing eventually, which we can remove. And then we end up with the right shape.
And you show in the paper that this is always possible, right? By an appropriate sequence of F moves.
Yes, which is exactly the sequence given in this figure. So you do each of these F moves, which will deform this snail-looking thing a little bit until eventually you're back into the right shape. And so if you add this snail, you do all these F moves, and then this snail just means this sequence of F moves. So this is what I mean when I say resolving into the lattice. It's just you do F moves in a sequence chosen such that eventually you'll end up in the shape of the lattice again. And then what we have written is a way to apply such a tube on one individual plaquette. So now that we have this, we can make projectors projecting onto the anion charge of individual plaquettes by just taking the right combination of these tubes. And by taking the combinations like these, of these the different kind of snails, let's call them, we can create projectors onto the different anion sectors. So, okay, so where does this take us? A little recap. So we have this model, which is anions on a trivalent lattice. We added these extra tail edges inside each plaquette. And now we have ways to associate the Hilbert space in which you satisfy all vertex conditions. We can associate this to a subspace, to this ribbon graph Hilbert space. So we can associate the subspace where no vertices are violated to a state which is some fusion state of anions of the doubled category. So we have a basis for the stringlet Hilbert space as fusions of anions. And we have a way to measure them, because I just wrote here the projectors you need to measure the anion content of a single plaquette. So with this information, in principle, we can see what anions noise has created and then recombine them. This is kind of the rough explanation of what is coming. So here is again this kind of projector. And so this sequence of F moves you must do to write this projector onto a specific anion content in a single plaquette. So we can write this as a quantum circuit. So you can write this sequence of F moves we saw before. You can write this as a very complicated quantum circuit because you need to redo the sequence in reverse for some technical reasons. And each of these blue blocks corresponds to one F move, which itself we can kind of decompose as a circuit involving only kind of basic operations. So we can do this, but that's not enough, because as I mentioned, this is all of this only works in the subspace where you don't violate any vertices. And well, you know, sometimes noise might get you out of the subspace. So since not every error necessarily commutes with measuring your vertex projectors, you can get out of the stringlet subspace. So what then happens is that certain vertices will be violated. And the idea here to fix it is that you measure your vertex operators, you check which ones are violated, and then you can do like a very small local correction, which will pull this violated vertex into the plaquette. So these tail edges come in handy to have, you will have some string, well, you have a chain of non-trivial qubits in your superposition somewhere. You have like a chain of 1 qubits, which will end in a vertex, and you will pull this into the plaquette. Well, you can do this with some small circuits. I won't list all of them, but they're all, I think the maximum depth is 5. So these are small corrections. And the only condition is that you first need to measure your vertex terms, and then you can correct them. So,
I mean, as a kind of moral question or like a conceptual question, I mean, of course, implicitly we are here in the digital world, so to say, because on the highest level, there's kind of 2 approaches to this, namely build the Hamiltonian and like recreate the analog Hamiltonian that hosts Fibonacci onions as excitations, and where you do the actual projections as like Hamiltonian projections of some type, or whether you use appropriate circuits to, in effect, measure the appropriate projections. And you go for the latter, right? Implicitly.
Yes.
And
yes.
that seems to be meaningful because the depth of the circuits is pretty small. And even if you have circuit level noise and so on, that shouldn't be the end of the world. That's basically the point.
It seems to be relatively manageable, but some more remarks on the circuit depth at the end. But yes, so yeah, again, this kind of is the same divide as I mentioned all the way in the beginning of this passive versus active approach. So the passive approach indeed to have some system which really realizes this Hamiltonian, and then you're kind of in the continuous case where you have these excitations which can appear and move around. But what we want to do is, well, here's a bunch of qubits on a lattice. If you measure this and do these operators, you can implement this code. This is kind of the thing we want to be able to do. Well, of course, it would be very hard to do any of this in practice because the circuits are still too long for what we can currently do. But at least in theory, it is possible.
Just a brief question. Since Jens was mentioning circuit level noise, have you thought about that at all? I mean, because I see that you have these like multiple controlled X-case, right? So if you have like some small phase errors or so, they will spread quite heavily.
Sure. Yes. So this is not something that we've done currently. I will mention this, like I think in the next slide even. We will assume at the moment that all circuits are perfect and so on. But this is like work in progress. This is like one of the follow-up research directions is indeed that this is not a fault tolerant setting. If you have measurement errors, if you have circuit level noise, I mean, we didn't speak about any of those. How can you, like, what do you need to modify and how can you deal with those? Can you make this into a fault tolerant code? It's like one of the follow-up projects that are happening.
So
but
just shortly, but
sounds really interesting.
So there is no fundamental reason why this shouldn't work. Like, I mean, there are all these, like, because once it could be, I guess, that if you don't push this red tail through perfectly, but like end up in a slightly different state, that what you do in the end then just doesn't make any sense anymore because it's sort of your description is wrong. Like you are. So is there some reason why this should be sort of, if you have some approximate implementation of this UV, or does one have to do the numerics and just see what comes out?
So this is indeed something we're currently like looking into. It is certainly like a complicated problem where your whole description breaks down once you get out of this subspace. In particular, will we be able to even simulate this? Because the only reason we can simulate this is because of some tricks which involve this precise description where we are in this string subspace. So it's a hard question and we don't have like the answer yet to that. Well, at least, of course, we hope there's nothing really fundamental here stopping us to doing this.
Okay.
I
mean, to be fair, I mean, any of these approaches will have its problems. I mean, even going back to your first figure, like when you go to a billion anions and magic state distillation or lattice surgery and so on, I mean, these overheads are also pretty huge and so on. So,
no, but there are different kinds of problems. I mean, one is the overhead and like resources you need, but the other one is sort of there. If the threshold theorem wouldn't hold, for example, then there would no way, like even,
that's right.
But it holds. But in this case, I mean, I hope something similar holds.
Yeah,
that
we think.
No, I see the point. I appreciate the point that one point is about overheads and the other one is about like making it happen for small noise levels anyway, so that errors don't spread all over the place. That's right. Yeah.
Yes, but indeed, it's an important question that needs to be solved. Whether maybe there is something fundamental making this impossible to become universal because you can't do this trick where we fix vertices perfectly. I mean, maybe we were looking into this, so I can't really give you a good answer here, but okay. It's certainly like an important question. So where were we? Right. So you can do these tricks to kind of fix violated vertices by essentially using these tail edges to kind of, you move all your problem to this tail edge and the reason that this fixes the issue is that this tail edge, has one end that's not connected to anything else. So you can just make strings end here. You can, you move all your problems there, and then they're kind of solved. But the cost for that, of course, is that now you have a non-trivial tail edge in this plaquette, meaning it can contain a non-trivial anion, which later you will have to kind of move to fuse with other anions you saw. So the error correction process happens in like a few steps. First, while noise is applied, then you measure all the vertex projectors and the tail qubits. So you need to measure the tail qubits to be able to do these vertex corrections as a unitary operation. So you also measure the tail qubits. Then you apply these vertex corrections if necessary. So once all of this is done, you're back in the stringlet subspace. So now we can understand things in terms of anions in different plaquettes. So once we're in the subspace, we measure the anion content of each plaquette by measuring these projectors I mentioned earlier with these snail-looking objects. And these constitute your syndrome. So your syndrome will be this type of anion is present in this plaquette, and this plaquette contains this type of anion for all plaquettes. And then you will feed the information to a decoder, which will decide which anions to fuse. And then once you've done a set of fusions, you need to do this again, because an important point about non-abelian quantum error correction is that your decoder must be iterative, because you cannot know fusion outcomes. So in the surface code, if I give you a syndrome in the form of these locations contain these type of excitations, like, oh, there's an E excitation present here, there's an M excitation present here, your decoder can do kind of like a one-shot thing where it says, if you combine all of these, all your excitations will be gone, and then you're back in the ground state if everything worked out fine. In this case, the decoder can't do that because it can't know for sure that things will cancel if you fuse them. So it will be this iterative process where you say, it will tell you, okay, fuse these pairs of anions, and then we'll measure the outcomes of that. And then we'll decide how to go forward by measuring everything again, and then we'll decide on the basis of this which ones to fuse now, and then you go on like this until everything is gone eventually, or you remain with like one anion left, and then you failed.
Okay.
So the way the decoder works, well, one of the decoders we studied, it's just a clustering decoder. So the way it works is that you kind of create clusters around each excitation you see, you grow them, and you fuse everything that you encounter. So this is a decoding graph. So every vertex here represents one plaquette on the normal lattice. And so anions now resides on the vertices of this decoding graph. So you draw these blue circles around every of your excitations, and you grow them by one step, and then you merge all of those that kind of touch each other. And then within each of these clusters that you form, you fuse all the anions inside them until there's only one left, or they're all gone. So between these two steps, some clusters, all the anions in them seem to combine to the vacuum, while in some clusters they seem to combine to something non-trivial. And then once this happens, you remove the trivial clusters, and you grow the non-trivial ones by one step. So the blue arrows indicate kind of how you grow these clusters. And then whichever clusters touch, you join, and then you fuse everything within them, and so on, until eventually all your anions are gone. Notice that, this is kind of a technical point about this. This decoder seems to care only about the location of anions. Because nowhere in these steps have I mentioned the specific labels these excitations have. This is just a property of this decoder.
But it could depend on that, right? I mean, this information that's perfectly available when you make the measurements of the syndromes, no?
Sure. Yeah, this is information that is available in principle. Just this decoder just doesn't care about it and doesn't use it. We studied other decoders that do use it, but these perform worse than a clustering decoder. We still assume that the optimal decoder for this, which we do not know, but the optimal decoder will probably use all this information, because there is more to know than just the locations. So the best case decoder should probably have some strategy which keeps in mind what the anion labels are of the anions that are being fused. But just the clustering decoder kind of by coincidence, I guess, doesn't care about it and seems to perform very well.
So just so that I understand correctly what you have in mind for like what an optimal decoder could use, are you also thinking about sort of knowledge about the noise model?
What I mean is knowledge about the specific anion charge. So we have four different anion labels that are possible.
Okay, because then, I mean, because the Pauli noise is sort of in this weird basis compared to the ribbon graph basis. I mean, a Pauli noise, if you know sort of it's a pure X error, you know, like it could cause some correlations between the anions appearing.
Yes, yes, you know certain patterns will appear, but the clustering decoder seems to be very good at detecting those because those patterns are always
local,
are very local. These patterns are specifically, here is anions in 4 neighboring plaquettes or something.
And
I'll show the patterns in a few slides.
Makes sense. That's quite cool. Yeah, I mean, makes sense because locally they also have to fuse to the vacuum anyway. So.
Yeah. So it seems that just the clustering decoder seems to be very well suited for this, but we still think that there must be some extra knowledge that could be useful because, there is more information available. So it seems that the best case would use all the information that is available, meaning also the specific labels of these excitations. The way in this this could be useful, although we don't know how this could be implemented, but if you look at the clustering decoder, so you'll see these patterns of kind of anions that appear, and you want to, if there's just here's a few anions and they're kind of remote from everything else, you will assume they were created together. But sometimes you can know they were not created together, because sometimes you can know their labels cannot fuse to the vacuum. There's some cases of labels where you do know the outcome, and then you could guess like, okay, well, this could not have been created together, so maybe we should kind of keep this in mind when trying to fuse them. But we don't know how to implement that properly. We did some attempts, but none of them seem to work to modify the clustering decoder itself. We have some kind of perfect matching type of decoder that does seem to work slightly better with this information, but it's a very slight increase in performance.
I see. The 2 questions on this. One is, I mean, that also seems to indicate that you could also think of more general errors in the first place, because if like correlated Pauli errors would anyway lead to some correlated patterns of anions, then you could also in the same way go for correlated Pauli errors, because I mean, either way, you will have some local like cluster of anions anyway, which you could presumably decode with your clustering decoder, right?
Yes, in principle, this should be possible. It will just be very hard to simulate. But
no, of course, I understand. But I mean,
but
from a kind of threshold perspective, this might work.
Yes,
and second,
yeah, this decoder doesn't care about how the noise appeared, right? All it knows is just, well, here's a bunch of anions. Now I will tell you how to fuse them. It was never told about how the anions came to be in the first place.
Okay, and the second thing is, I mean, like, why did you resort to the clustering decoder, not minimum weight perfect matching in the first place? That seems like more canonical or standard. Like, there must be a reason for this.
The more, yes, there is a very good reason for this. Is that the more, if you just take perfect matching as a given, this has no threshold in this case, and this is provable. The reason for that is that this is a non-cyclic anion model. No, sorry, this is a cyclic anion model, meaning I can have 2 excitations which can fuse to themselves in a sense. So if I have 2 tau anions, for example, they can fuse to a tau anion. And this specific property will cause the perfect matching to fail. So yeah, perfect matching, I can show you some figures later at the end maybe from the paper, which if you make some figures, you can see that you can create situations very easily where perfect matching will just stretch out errors and create like very large, yeah, very kind of spread out pairs of anions, which is exactly what you want to avoid.
Fair enough. Yeah. Okay.
But we did successfully manage to kind of have a slightly modified version of perfect matching. So something based on perfect matching, but not quite the same, which has a threshold, but it's still lower than the clustering. Clustering just seems to work very, very well in our specific case.
Okay, wonderful.
Okay.
Just a small comment on that. I don't know if you are aware of this, but there's this work by Ben Brown and others on like how these matching algorithms can be viewed as sort of a relation among the stabilizers. And because they assume abelian stabilizers, they like this is a proper like sort of a group like a relation. And I guess in your case it would be kind of extended. It would be extended to an algebra, and so instead of having sort of a relation, all the stabilizers multiplied together yield the identity. In your case, would be something like decomposing into different terms. Did you think about this decoding problem in this
Not
way,
yet.
or okay?
So I don't have any answers to this. It's a very good question, but I don't know how this would work in our case. It's certainly an interesting thing to look at. I mean, there's many kind of possible directions to go, and this is certainly like one of the things to study in the future, but that hasn't happened yet. Okay, so let's do a very short recap of what we've seen so far. So we have this code, which is qubits on a lattice. It's on a trivalent lattice. We added these tail edges everywhere. Then we can define some code space by saying, okay, well, you measure these vertex terms, you measure these plaquette terms, and this defines a code space. Then we saw that if you limit yourself to the subspace where all the vertices are satisfied, so all your vertex conditions are satisfied, then you can understand states in here as fusion states of anions or linear combinations of such states. And this allows you to do quantum error correction by, understanding the anion content of a certain excited state by measuring it, because we could define measurements which measure the anion contents in a single plaquette. And this information can be given to a decoder, which will tell you how to fuse anions to kind of get back to your initial state. And as a kind of an extra little thing, we had to correct vertices whenever these are violated. So sometimes noise will take you out of this subspace. Then you measure the vertex terms and you apply these small local corrections to get you back to the stringlet subspace. And then you're kind of back to your usual thing where you measure all the anion contents, all the plaquettes, you measure their anion contents, and then you give this to a decoder, which will tell you how to fuse them. Okay, so with this behind us, the question becomes, okay, well, what's the threshold of this code? Can we classically simulate this with a given noise model and find a threshold? And the answer is yes, and I will tell you how. So, so the big question here is, how do we translate noise in terms of just errors on individual qubits? How do we translate this to processes involving the creation or the movement of anions? So as I mentioned before, since this is a non-stabilizer code, Pauli noise is not the most natural choice here. Well, most natural in the sense that it's convenient to work with. Since things in stabilizer codes, things typically just commute or anti-commute, and this gives you pretty clear relationships in terms of what kind of excitations are created by what errors. This is not the case at all here. We still use Pauli noise to kind of have a comparable benchmarking, let's say, of the code. So fusion states of anions in these plaquettes correspond to this unique lattice states of qubits. We discussed this before, but these are these highly entangled, very complicated states. These states formed an orthonormal basis of this subspace. So what we need to do is essentially a basis transformation kind of thing. So we need to express the joint action of the noise, the fixing of these vertices when necessary, and of these vertex corrections after you measured the vertices. We need to kind of express this whole thing in a different basis. The problem is that this basis is very complicated. So let's first see what happens when I when I apply noise on a state to kind of see what we exactly need. So I have some initial state, which I will express here as a linear combination of fusion states of anions with different weights. So these alphas are just weightings on superposition, and I sum over all possible anion states in different plaquettes, kind of all possible fusion states. So I apply noise to this state, some Pauli error, for example. So I pick a qubit, I apply this random operator. So now I have the following state, which is just the same as the one before with the sigma written here. So what I want to do is I want to measure all the vertex terms and all the tail measurements, all the tail qubits, and I will find some outcome with a certain probability. And this probability is given by the following expression. So what I did is just I have my state, I take a bra and a cat, and I put in between of these just Pauli error, projector on some measurement outcome, the same Pauli error again. This gives me my probability. So to express this probability, in general, what I need is these matrix elements. So it's the sandwich of this thing in the middle here between basis states in the form of fusion states of anions.
Does P sub V include the vertex correction? Like
No,
because
not
within
yet.
each measurement outcome subspace, it's a unitary, right?
Yeah, it is, but this is not included in this P. This P is purely just, here's a projector on a measurement outcome. Because you will need this to be able to kind of sample correctly what your probability is.
Right, you sample if you
so
get a non-trivial vertex outcome or not.
So this is purely a projector on some possible measurement outcome. So this V represents the joint measurement outcome of all vertex measurements and all tail measurements. So after you measure these things and you find a certain outcome V with this probability, you will apply this correction. So the state after this is, you have your state, you apply your Pauli error, you apply your projector on your measurement outcome, and then you apply your correction, and you normalize the whole thing correctly. So, we can just re-express this whole thing because we're back in the string at subspace here, right? So this psi2 is some state in the string at subspace because we fixed the vertex violations with this U. This U is this small unitary. So we can re-express this whole thing in terms of a linear combination of fusion states of anions. So we can just expand in this basis by adding some identity in the middle here. So we have two types of things we need. The first is these matrix elements of sigma, PV, sigma. And then we need matrix elements for U, UV, PV, sigma. Well, this small v here needed to be capitalized. It's a small typo, it seems. But yeah, so you just have two types of matrix elements. And if you have these, you know everything there is to know for your simulation. Well, everything you need to know to build your simulation, let's say. The problem here is that these matrix elements are tricky to find because these basis states are very complicated, right? These basis states are these highly entangled states of all these qubits in your lattice, and they're all super entangled. So the solution to this is that we will use tensor networks to express these states. So these matrix elements, specifically kind of the states, you take a basis state and you apply either noise, measurement, and correction, or just noise and measurement. These matrix elements only depend on some local properties of these basis states, in the sense that whatever matrix elements I'm calculating here should not depend on what is happening far away, right? If I have, whatever is happening far away from this thing around this error shouldn't matter for these matrix elements. Because more technically, this sigma x here, for example, is commuting with some operators far away. Just if I look far away enough, this all commutes with the sigma x, right? The only things that do not commute are just measuring the anion charge very nearby, for example, or measuring the vertices very nearby. So given that it only depends on local things, we can even look closer and say it only depends on the direct neighbors, and we will write this in kind of these fixed shapes of these fusion trees. So for example, the sigma x, as is given here, only depend on the anion charge of these 4 plaquettes, on their total charge of the 4 together, and on the way these fuse. So the way these fuse will give you this label kind of B1, B2. The total charge of all these 4 plaquettes will give you B3, and then A1, 2, 3, and 4 are the anion charges of the 4 plaquettes involved. If you have some different orientation, you have a similar thing with either 2, 3, or 4 plaquettes that are involved. But these are kind of all the possibilities here. If it's a sigma z, it's even simpler. Then you can only have two plaquettes that are involved and their total charge. So what we can do now is express these basis states. We don't need to express like the most general basis states here. We can assume that it's just in the trivial state everywhere else, and the only excitations we need to look at are those right around the error we're studying and kind of their total charge, but that's it. So we can write these states as a very nice tensor network, assume it's the ground state everywhere else, and then just focus on the middle part here. These tensor networks come out of this paper of Nick Butling and collaborators.
Could I ask a question?
Of course.
So this UV, on which edges could that operate? And is it given that whatever you find for UV also commutes with plaquettes that are not labeled here?
Okay. Yes, let's go over like the specific case here, and then kind of, I think that will kind of give a general impression. So imagine I start in the ground state and I do this 1 sigma x error on the edge. I don't know if it's very visible, but there's like one blue edge.
Yeah, yeah, I can see it.
Okay. So if we just look at the vertex projectors, well, they're not written explicitly anywhere here, but the sigma x doesn't commute with 2 of the vertex operators here, just because it's only involved, this edge is only appearing in 2 of the vertex projectors, being, the 2 that are connected to this edge. So you can see my mouse, right?
Yes. Okay, I see the two vertexes.
So there will be kind of these small local corrections happening in 2 places, happening kind of here, involving these 3, and involving these 3.
So for me, the mouse seems to be shifted.
Yeah.
I think you mean like just the ends, the 2 vertices at the ends of the blue edge, right?
So it's okay. Yeah. So the 2 vertices that could potentially be violated when you measure them after this error has been applied are the 2 ones connected to this blue edge.
Okay. Yeah.
And then when you do the correction, if one of them is violated, you will pull it into the either A2, like the tail in plaquette A2, or the tail in plaquette A4. This is where you will pull this violated vertex kind of into. And so it commutes with everything else. Everything far away is all still safe. It's just plaquettes A2 and A4 that are affected here. And the vertices connected to the blue edge.
Okay.
So so these fusion states of anions admit this very nice tensor network representation, which keeps the structure of this fusion tree. So yeah, you can just derive it. Well, I want to go over the details. If you want the details, it's in the appendix of the paper. But yeah, you can just straightforwardly kind of derive this tensor network representation, and then we know we can write these states, like this specific state, as this tensor network. And now we're in a much better situation, because we can find this overlap as some contraction of a tensor network. So we will switch to a square lattice, which you can do by kind of grouping vertices in a way that gives you a square lattice, because it's handier to work with. So if we start with some state of 4 anions in 4 plaquettes that fuse to some total charge, which we hide in a next, like in a neighboring plaquette somewhere. That's one of my basis states. And then I start with this state. I apply my whatever thing I want to measure the matrix elements of. So I will kind of do noise, project it on some measurement outcome, and then this sigma on top of that. And then I will sandwich this whole thing with another of these basis states with different labels. And then I have this big sandwich, which I must just contract as a tensor network. And because I'm free to assume that everything else is in the ground state, I can use these tricks where I find fixed points, and then I can kind of do this infinite contraction as a finite contraction, and then I get these matrix elements. So this gives you a trick to find these matrix elements. And with enough patience, you can compute all of them. I don't know anymore how many there are, but a few hundred millions, I think. Many of those are trivial, however.
I see, but I mean, like, of course, these are all like MPO injective PEPs because you're coming from the Levin-Wen picture and so on. So the symmetry objects are MPOs themselves. But here, that's of no concern whatsoever, right? Because you just really compute matrix elements of a small patch of a PEPs with certain boundary conditions. So the gauge or the MPO injectivity or so doesn't matter whatsoever. It's just a small PEPs computation. Is that right?
It's just as a relatively small PEPs computation. I mean, all of these has very high bond dimensions, but are very sparse.
Sure.
You can try to work around the high bond dimension by the fact that these are extremely sparse.
I see. But even with brute force,
it's a big contraction to implement, though. I mean, because there's many indices involved. Because the square is just a fancy representation of objects like these, which are pretty involved to write out completely. But I mean, it can be done. You can contract this, and you can use these tricks where you find the fixed points on top, bottom, and left and right, because you can assume the ground state kind of everywhere else beside a small region. And then you can compute your matrix elements. So once you have these, you can in principle simulate the whole thing classically, under the assumption that all gates are perfect and so on. So in general, there's another concern though. That is that, we're trying to simulate universal anions doing things. Shouldn't that be the same as simulating a universal quantum computer? That's like a kind of important question here, because if you can simulate the most general thing about Fibonacci anions, you already have a universal quantum computer. So we at least we hope that this shouldn't be able to be done. That one shouldn't be able to do this on a classical computer, right? My desktop shouldn't be able to simulate a universal quantum computer, or at least we hope. So
I'm not fully following. I mean, there's a bit like for measurement-based quantum computing, where we know that, of course, PEPs contraction is sharply hard in worst case complexity and so on. But of course, you can still like classically efficiently think of computational models and do everything except the last little step of contracting the full tensor network that would give rise to the solution of the decision problem. And that's probably the same for you, no?
Okay, so maybe I wasn't completely clear about this. This isn't necessarily a tensor network problem. This is rather that, we're trying to simulate a model which involves universal anions. And we do not expect the universal dynamics of Fibonacci anions to be classically simulable, because that amounts to simulating a universal quantum computer.
Okay, fine.
So yeah, this maybe for a bit like too short between these two things.
Okay,
but yeah, it's like the tensor networks allow us to compute these matrix elements. So in principle, we can do the simulation, we think, but then we must ask ourselves, can we really do this simulation? Because we're simulating universal Fibonacci anions. However, we're not simulating the most general process here. And that's kind of the way out of this problem. Because we expect, well, most naively, you expect things to scale horribly. But there is a way out of this, is that instead of simulating the most general dynamics of anions, we know that noise with local errors only creates these small groups of anions, which are themselves completely kind of unrelated. They never met each other. So the braiding statistics between these distinct groups can be ignored.
But you still have to compute these matrix elements on the fly, because it's a non-abelian model, so you have not this guarantee that like an X error acts the same on a state where an X error has happened before compared to it where it hasn't happened before, right?
Yes, that is an excellent point, and I will come back to this in a second.
Oh.
Yeah, we will need to do some light cheating, but we will. Yes, I will come back to this, and it will become clearer. But yeah, okay. So in principle, if you have separate errors happening, these clusters of anions are kind of distant, have never talked to each other. So the whole fusion space factorizes into smaller blocks. So instead of needing to keep track of the fusion space of all anions that have been created, we need to keep track of a bunch of little fusion space separately. And as long as these don't connect with each other, we're fine. And we know that below a certain error strength, which we call kind of the percolation threshold, below that one, things do not percolate, in the sense that you do not connect all these individual groups. They stay disconnected. And we know that beneath that limit, the largest group that you encounter scales as log L, where L is your system size. So instead of everything scaling exponentially, we have the resources you need to simulate a group of n anions scales exponentially in the number of anions. But the number of anions you need to simulate scales logarithmically with your system size. So these things just nicely cancel out, such that you can simulate the dynamics of the anions appearing because of this noise in a polynomial time. So
what did you do? Did you like sort of for sort of you say, okay, I have my simulation in mind, and I think that the largest cluster that will appear is sort of size 10. So do you then compute all the matrix element for all possible cluster configurations of size up to, I don't know, 13, and then you keep them as a lookup table, and then during your simulation you just look them up? Or is it really that you calculate them on the fly to not have huge storage wasted, because most clusters will be small?
Okay, that is truly an excellent question. So what we do is we compute them all of size. We do all the size 1 and we compute all of them. And we will, as you'll see in the next slide, we will make some assumptions about the way in which the noise appears, that this is kind of the legit thing to do. So we compute all of them of size 1 and then have like a lookup table.
With size 1, you mean sort of the elementary fusion tree of like, but
yes, so at most
has 4 plaquette labels
are involved. Yes, in principle, to simulate the most general case, you need to kind of do all different sizes, and then be able to you need to find some way to compute those on the fly. It's not a thing we have figured out how to do. And so we'll make some extra assumptions, and I'll make some more remarks on that in just a second. So the classical simulation works as follows. So we assume that noise are like random Pauli errors. And then what we do is we pick the total number of errors from some Poisson distribution. So we assume each kind of the noise on each individual qubit to be like a Poisson process. So the total number of errors can be sampled from this Poisson distribution. So you say, okay, well, this round of our Monte Carlo simulation will pick T errors in total. We assume perfect measurements, we assume perfect recovery operations, and then we do the following. So we simulate for T time steps the following thing. You select some random edge. You apply this Pauli error to this random edge. Then you measure all your vertices. You fix all your violated vertices. And then you measure all the anion charge of all these plaquettes. So this is kind of the situation where you're constantly measuring everything while noise is happening. And we assume that we can measure much faster than the noise is appearing. So we assume very fast, well, we assume instantaneous measurements essentially, and perfect measurements. So you're constantly measuring while this noise is happening. And after T steps, we correct. This is kind of the assumption. And so this is why we get away. This is why we get away with only having the matrix elements for individual Pauli errors. Because indeed, in general, you need any chain of Pauli errors.
Well,
this,
or a way to concatenate two length one
yeah,
chains.
there is no known way to concatenate, indeed. So,
Yeah.
so
but only for the Fibonacci model, right? So only for non-abelian models, because for abelian models, I think it should, like,
yeah,
I thought it was possible.
Yes, for abelian models, as far as I know, at least, we can concatenate because, well, for the surface code, for example, we just know, right? If you have 1x error, you create these two anions. If you have 2x errors in a chain, well, you just have these two at the end, because we know what happens kind of if they meet. But we don't know what happens in this case. So yeah, one possible kind of research direction to address this issue, because yeah, I mean, we cheated in a way, right? Because we assume these instantaneous measurements all the time. So one way to address this would be to add a lookup table of all the kind of the two chains, the chains containing two anions, well, two Pauli errors, I mean. So then you have a bit more of a general table where you allow size 1 and size 2. And then you can see if that makes a big difference for the threshold. So you can say, imagine we allow up to, you know, a certain size. And then we can see if that influences the threshold. We think it will have a minimal influence because these events are rare anyway. It's in general pretty rare that neighboring edges are selected at random if you apply only very kind of sparse noise. So this is why we think this should still work. I mean, why the threshold is still valid, because the events in which you connect neighboring anions and neighboring edges with your noises are pretty rare. Okay, so
I see, but I mean that says little about the fault tolerant regime, right?
yes, indeed.
This might be entirely different. I mean, I'm not criticizing this. I mean, it's beautiful work, not denying. And
sure.
was a bit of a smart-ass comment to.
Yeah, but these are kind of important questions to address. I completely agree. These are certainly things that we need to work on in the future. This was just kind of a first step. There's a lot of open questions on this.
Wonderful.
There seems to be not too much work that has been done on like microscopic models like we had for non-abelian anions. There's some work on these phenomenological models, but very little on the situation where here is some lattice, some qubits on a lattice, here is some noise model, and you know, we choose our measurements such that this is a non-abelian code, figure out the thresholds. There seems to be very little on this. So there's a lot of open questions. Okay, anyway, so with the assumption we made before of kind of these T runs of errors, the constant measuring in between, and then at the end of this, we can apply our decoder to correct, we see kind of the following relations between physical error rates and logical error rates. And there's these very nice crossings in both cases. We have like a very distinct intersection here, which we interpret as our threshold. There's different ways to see a threshold in this, but this is kind of the most straightforward. You draw these different curves and you look at the intersection. And so we know that below this value, we know that if you increase the system size, your performance gets better, essentially. And we can also show that it gets exponentially better in the system size. So the thresholds we find are surprisingly high. We expected there to be a threshold, but this is of the same order of magnitude as the surface code, which is relatively remarkable given that this is such a complicated model. You know, noise doesn't just create pairs of anions, but can create like quadruplets of anions. So noise can, you know, the anions spread really quickly in your lattice because you create quadruplets of them that don't necessarily fuse back to the vacuum if two of them meet. So yeah, we have a surprisingly high threshold, but of course there's some work to do in terms of a fault tolerance setting and in terms of allowing longer error chains in our simulations. Okay, so let's finish this with a quick summary of the whole thing. So we want some active non-abelian continuum correction. So we have a system of qubits on which we measure some operations, some projectors to define a code space, and you want to do continuum correction in there. So the code space is defined as a modified Levin-1 Hamiltonian, as a ground space of a modified Levin-1 Hamiltonian with these tails in every plaquette. So we kind of combine for this quantum error correction as a whole, and then topological quantum field theory to figure out this tube algebra, which allows you to measure the anion charge of individual plaquettes, and to figure out this anionic fusion basis, which allows you to describe excited states in terms of anions. And then we use tensor networks to understand what errors on the level of single qubits mean in terms of anions being created. And by combining this, we find, as far as we know, the first threshold for a 2D code which natively supports universal quantum computation. By natively, I mean like no code switching, no magic state distillation. And on top of all of this, this threshold is in the same order of magnitude as the surface code, which seems very promising. So yeah, as an outlook, as like future directions to go, different noise models, of course, a fully fault tolerant setup where we allow measurement noise, a circuit level noise. So this is a project that's kind of currently going on. Different decoders, because it seems that this clustering decoder, as I mentioned before, isn't using all available information. So there must be some it seems to us that there must be something better using more information than just the location of anions. Then, well, this is like one specific non-abelian code. There's others to study. There's models based on the quantum double, for example. There must be other non-abelian models which have better properties for this, by which I mean that the circuits are lower depth, for example, because the circuits we need are relatively high depth in the end to measure, specifically those to measure the anion charge in plaquettes. We think there must be models which are still have all the properties we need to do this universal computation within the code space, but have better properties for the error correction, specifically for like the fault tolerant case where you stop assuming that everything works perfectly. Well, we could look into like boundary conditions of this, because all of this needs a torus, which is not something you typically want if you try to make this in the lab. So it's looking at non-abelian codes with boundaries. Like another direction is, if you think about implementation, is this efficient multi-qubit gates. So the circuits we needed have this multi-qubit Toffoli gates that we need to implement these F moves efficiently. If you could do this as like a one-shot efficient thing on the hardware level, this would greatly improve kind of the circuit length, because you cut your circuit length by 6, I think. So that would be pretty good as well. And then, of course, as I just mentioned before, in our simulation, allowing longer chains of errors to happen and see how this influences the threshold. Okay, and that's that was it. Okay, so I would be happy to take more questions or to discuss more things.
Wonderful. Thanks so much for this highly inspiring talk. I mean, as you can see from the many questions, you've hit a nerve here. That was great. I'm sure there's more questions. I have some. I mean, it's already quite late also, but I'm sure we have more questions. Who wants to start?
Yeah, so I have first 2 questions, like one just from this, actually for the measurement circuits, which is a bit more concrete, and one concerning the boundaries, which might be a bit shorter. So I'll ask that first. So you mentioned, okay, maybe different bracket simpler non-abelian codes. So as far as I know, the plane, like the double Fibonacci phase has only a single boundary, so you cannot really think about having a surface patch. Yeah. What kind of planar encodings are you thinking about? Like, because you could think of twist effects and such things, but they might be even more complicated than the model.
Yes. So at the moment, like very concretely, none of them, because this is not a thing we've really looked into much. But yeah, twist effects are like one thing that is certainly like within the realm of ideas we have of studying this, but hasn't been done concretely. And you're right about the Fibonacci phase not having the rough and smooth boundaries. Like you can't do the same tricks as you do with the surface code for the Fibonacci case. So yeah, I don't know about other models where this could be possible. So this is something I still need to kind of read up on.
Okay, cool.
Yeah.
I
so
mean, we might be
able.
We might be able to calculate the existence quite. Like, yeah, we have some ideas on similar, like not similar models, but other models. I think the techniques would apply quite straightforwardly because it's a string net description. So
this is what we hope. Kind of one of the things we hope out of this paper is that this also maybe carries over, all the techniques that we use carry over to different models, so that this must not be like the one and only non-abelian code that's studied, right? We hope people will start studying different non-abelian codes, but these tensor network techniques, for example, seem to be pretty universal in the way they can be applied, because the same underlying kind of rules seem to be applied in each non-abelian code. So yeah, I would be very interested to discuss actually later if you want, if you have some specific ideas in mind. Maybe we could discuss the way in which some of these tricks carry over.
Yeah, we're discussing anyway soon on this. Yeah, that's good. But you had the second question, right?
Yes, on the measurement circuit. So you showed this slide with like blue bars representing these F moves, and you called them the circuit representing the POVM you get out of this tube algebra, right? But as far as, like, for me, the circuit just looks like one term of the projector, which is like a sum over F and so on. And so the circuit just is a particular term, but like the full POVM would really be, I don't know, like a circuit where measuring a binary outcome then relates to the different spaces.
Okay, very good question. So the the circuits just excuse me, like what we call here the grow circuit, like in this dotted box, this is precisely this thing. So this is indeed one term of kind of one term of this projector. The fact that this is the whole projectors is hidden inside these U's. Yeah, I would be happy to discuss this later. I don't know how much kind of time and patience other people on this talk about on this meeting have, but yeah, the kind of the fact that this is the whole POVM is hidden inside these two U's. It's kind of hard to show just with this drawing, I guess.
I see. And you use 3 ancillas for the measurement. Do I see that correctly?
Yes, that is correct.
Okay, so but you just have like a 4-valued outcome. Why do you need 3, which would
okay, let me switch from the slides to the paper, and because there is a very specific, like, we address this point precisely somewhere. Let's see. Can you still see my screen, by the way? Because I don't know how I set this thing up.
Yes, we can.
Okay, very good. Should be hidden here somewhere. There we go. So the way we should think of this, you can think of kind of this whole blue circuit that was in my slides, kind of this whole thing, as follows. You start with some bubble, and you stretch it out, and then you kind of get this double Snell thing. So this double Snell kind of looking thing is what this circuit does. So this seems slightly different from the one I had here, right? Because this was like you glue one of these things and you do these F moves. But the result will be the same. The result will correspond precisely to doing the projectors you need. You can get these red projectors by, yeah, well, this is like a very technical thing to go into, of course.
Well, but I think
But
I
yeah,
got a better idea. So you basically push this outcome sort of 1 1 tau 1 tau 1 tau and tau tau into the computational basis state of some ancilla and then you measure.
yes, but this is precisely what we do. This is exactly what this is. So if you do kind of this most general thing here, where you have this bubble that we stretch out to get this double Snell thing, if you then are able, well, this is kind of the most general thing, and all possible outcomes are hidden in here. So what you do is you do this one, and then you measure in the right basis, and that will precisely project. Well, the whole POVM is it's all kind of detailed more in the paper, or specifically on page 16 on the archive version. But yeah,
cool, thanks. And I think I got a quite better idea now. That helped.
See it in the equations precisely, but it's as you said, by doing this sequence of F moves, you can read off the precise anionic excitation, the label, by doing a measurement on these ancillas. This is what this circuit does.
Okay.
Yeah, and the measurement basis is specifically this one. And you can, and well, we show here that this is equivalent to measuring these projectors, that this is precisely what is happening. But yeah, I would be happy to discuss this slower, maybe, if you're interested afterwards.
Yeah, that's a very interesting point. Indeed. When you say that you've looked at well, these specific models, but also other models would work, like quantum doubles and so on. So I understand this would, I mean, this whole framework would in principle work for all like codes derived from 11.1 models when you have like an MPO objective tensor network picture behind, right? So in principle, this should still work. And when you say that this has particularly nice properties, you mean that specifically in relationship to the circuits that you need to perform the respective measurements? But of course, there's also other things coming into play, like the detail of the threshold, right? I mean, could there be like trade-offs in the threshold compared to other complications like circuit depth or so? That's the one.
Well, I suppose they are. I mean, we haven't studied these different models yet.
Okay.
But yeah, I mean, maybe that's certainly a thing to look into. I mean, of course, we hope not, right? What would be like the best case scenario is that you find a model with much shallower circuits, which still has a good threshold. This would be the dream, but
okay, sure. No, of course, we are all young enough to dream, right?
Yeah, I mean, someday we'll know.
And I mean, also like ideas like single shot error correction and so on. I mean, surely one can think about them, but it's far from obvious how one would do this, right?
Yeah, just there's a lot of directions to go we haven't explored.
Okay.
Well, but just in 2D, I mean, just in 2D, single shot is not, at least not like if you have a TQFT model, it won't ever be single shot.
That's right. That's right. I mean, okay, if you're in 11.1 world, then that's right.
I had a question about the threshold. So I understood that you calculated them using these plots, but there has been work by Chris Chubb, which involves taking a Hamiltonian and finding an equivalent statistical mechanics mapping, and then associating the threshold to a phase transition in a classical stat-mech model. Have you considered doing something similar for your non-abelian models?
Yeah, we have, I mean, I at least have tried to do this at some point without success. So the issue here is that the tricks that are used to do this, because the first case that I know of where this was done is the surface code.
The work by Dennis, right? Yeah. No.
So and then there's this paper indeed by Chris Chubbs, which generalizes this to other abelian codes, I think. But it seems that almost none of the tricks that are used carry over nicely because things don't just commute or anti-commute. Since this is not a stabilizer code, well, I mean, you could call this a stabilizer code in a way because they're like commuting projectors, but yeah, they're not just Pauli's. So things don't just commute or anti-commute. And then most of these tricks seem to break down. But it's certainly a thing I hope to find out. Like, because this is the thing we showed here. This is not an optimal threshold. This is just, you know, this decoder gives us this threshold, but there might be better decoders. So if you could map this to some stat-mech model and then understand the threshold as a phase transition, then you can have like, this is the optimal threshold. That would be very interesting.
Mhm.
Yeah.
And I really
So-
hope to find out how that works, but I don't know yet how this could be done.
Yeah, so when Chris Chubb was giving a talk about his two papers a few months ago within this seminar, sort of, his suspicion, because he also he said that he thought about it, and his suspicion was that instead of being I mean, this should maybe not go into the YouTube link later, but like his suspicion was that it won't be a classical statistical model just because of this non-abelian nature, but could be some quantum statistical model. And then it's, again, maybe hard to find a phase transition or something.
Yeah.
This is just a comment I remember quite
Yeah, that
clearly
seems
from
like
a discussion with
a
him.
reasonable idea, even though I don't know,
Yeah.
I don't know how this mapping would work. Yeah, I know several people are interested in finding this, because I've talked with some other people as well. But and it's like one of the things I plan to look into more seriously in the near future. But at the moment, I have no idea how this should be done, and if it's possible at all.
Cool.
Fair enough.
Yes.
One other question from my end, if you go to your Outlook slide, there
we go.
Yeah. Okay. Cool. So you talk about applying your. So I think this is your fourth point, in which you said that you want to apply your techniques to different non-abelian codes with possibly with lower depth measurement circuits. So I'm just wondering, like, for any given non-abelian model, like, do you have some property in mind that from which you could infer that the measurement depth circuit that you would have would be of lower depth?
Nothing specific at the moment, but one thing that comes to mind is be able to have square plaquettes. Seems helpful, because now we have all these hexagons, which means you'll have, well, this whole anion charge measurements involve just more qubits. So just smaller, just if you could have a square lattice, that would be a start, I guess. But more in general, no, I don't know yet. Like, is there a way? It would be interesting even to kind of reverse this, I think, and to find out, okay, can I construct, if I know property, like what are the properties I need from circuits to construct a non-abelian code? I don't know if that's even possible, but that's like a very vague idea of, like, could I find an abelian code specifically based on I want circuits to have like at most these lengths? How could I find a non-abelian model that works for this? Like there's just like a ton of directions to go, and most of them are just completely unexplored as far as I know.
Yeah.
Do you think that
makes sense to say this, but like maybe it just depends on the property of the group, right?
which group?
That you put into your non-abelian or your abelian model.
Well, Fibonacci has no group in it.
But I'm saying, like, there must be some sort of algebraic property that determines whether or not you have a low depth measurement circuit.
I mean, maybe I can phrase my question here. I had for the similar things, which is that because, I mean, you write down the projectors of the tube algebra, which then constitute your pure VM, and there this nasty phi appears, right? This golden ratio. And I mean, there you sort of, for me at least, kind of intuitive that it's hard if you want to sort of have an irrational number appended, that it's like if you write a circuit that sort of appends this based on Pauli's, Clifford's, and so on, that this could be hard. Like, are there, does it make sense? And if so, would other non-abelian anions which would not involve these specific numbers maybe easier? Like, I don't know.
Yeah, it's a good question, but I must admit I don't know.
Yeah.
Yeah, let's take a look at the circuit.
Yeah,
again.
just realized that it's also not so clear as I had it in my head.
No, I think I see your point. But I don't think I know.
I see.
How it should be done. I mean, what would be a huge step forward, but this is kind of a different solution is as I mentioned, these if you have very efficient Foley gates on multiple qubits, this would also help a lot. If you could do like, already like this 3-qubit, like this double control C0s, that would help, but this is a different thing. Yeah, I don't have an answer to your question, sadly.
Okay, wonderful.
I mean,
Good.
maybe it would just be interesting to have sort of the simplest non-abelian quantum doubles and then just write out the tube algebra explicitly and see how it looks like, because I think that besides S3, I haven't seen the idempotence worked out explicitly.
No, neither have I.
Yeah.
Shall we maybe discuss this in the crowd that we have anticipated soon? Because like, I mean, it's already like 5 something, and maybe we should kind of move to a smaller crowd soon and discuss these details. It has been enormously productive and stimulating. It's great, but maybe we can call it a day, and then even more looking forward to further discussions. There's a lot of directions that.
Yeah, there seems to be a nice crowd also to discuss these things with. Yeah,
That's true.
I'd be very happy to discuss this more.
Wonderful.